Alright, finite differences. Those are the differences in values for successive table rows. Differences in values. Successive table rows. So when you're using a table of data, you can use finite differences to determine the type of function the data represents and to write a function representing the relationship between the variables in the table. So we're going to figure out, is it a linear function? Later on we'll talk about exponential and if it's a quadratic. But one thing I want to go over is f of x equals mx plus b. So I want to remind you guys that in this equation, m is equal to the slope or the rate of change. And then b is either it's the y-intercept. But it's also known as the starting point. It is where, if you have your graph right here, it is where your graph passes your y-axis right here. That would be your b. So then, as just a reminder, slope is your rate of change. So I'm going to make sure to write it right here. Because sometimes the rest of this might not call it slope, it's going to call it the rate of change. And if you have your coordinates x1 and y1 and x2 and y2, then you can find your slope or your rate of change by finding the difference in y over the difference in x. Delta y over delta x is difference in y over difference in x. And that's just going to take your y2 and subtract your y1 and divide that by x2 minus x1. And y1 and y2 would be their first coordinate points. So you're going to take the y value of your second coordinate point, subtract each other, over taking your x coordinate points, the second ones minus the first one. And you could flip them, whichever ones you pick, just keep them in pairs. Okay, so for an example, pencil. Where did I put the pen? There it is. Okay. So, finite differences. We're going to find delta y, the difference in the y's, and the difference in an x as table values. So the difference in this x, delta x, would be x2 minus x1, which is 1 minus 0, which just equals 1. So that would be in the denominator. Right here, on our numerator, we would have y2 minus y1, which is b plus m minus b. You have a positive b and a negative b, and those cancel out, and that just leaves you with m. So then the rate of change between these coordinate points is going to be m over 1, which is just m. Alright. A quicker way is you could find them each, or you could just check and make sure all of your delta x's equal the same and all of your delta y's equal the same. So as we go down, the delta x of this next point would be 2 minus 1, which is just 1. The delta x of this point would be 3 minus 2, which is 1. And the delta x of this point is 4 minus 3, which is 1. And the delta x between these two x values would be 5 minus 4, which is just 1. So notice that all your delta x's are the same. And doing all the delta y's, this would be b plus 2m minus b plus m Distributing that would give you b plus 2m minus b minus m. Positive b, negative b cancels out to 0. If you have 2 m's minus 1 m, that leaves you with just 1 m. That would be the same as having 2 apples and giving away 1 apple. M is just a grouping. Okay, so far our delta y's are the same. Checking the next one. B plus 3m minus b plus 2m would give you b plus 3m minus b minus 2m. Again, the b's cancel. 3m minus 2m is just m. So far, so good. The next one, b plus 4m minus b plus 3m is equal to b plus 4m minus b minus 3m is equal to negative b and a positive b cancel out. 4m minus 3m leaves you with just 1m. And checking the last one, so far our delta y's are all the same. We would take b plus 5m and subtract b plus 4m to get b plus 5m minus b minus 4m. So then b and negative b cancel out. 5m minus 4m is just 1m. And all of our delta m's have also stayed the same throughout the whole thing. So a thing to note right here is that all your delta x values are 1. And all your delta y values are m. This tells us that the finite differences are constant. If you found each slope m over 1 is m over 1 is m over 1 is m, continuously on, then the slope is the constant throughout this whole entire set of data. And so it would be a linear function. So in conclusion, for finite differences and linear functions, we have that in a linear function, the finite differences between successive y values, which are known as delta y, are constant if the differences between successive x values, which are known as delta x, are also constant. So all it's saying is that if your finite differences between your y values are constant, and all of your finite differences between your x values were all constant, if you get the same all the way down on both sides, then you're a linear function. And then if the finite differences in a table of values are constant, then the values represent a linear function. And again, all this is saying is that if all your delta y's are equal to the same thing and all your delta x's are equal to the same thing, then you are a linear function because you have the same exact rate of change throughout the whole entire function, and linear functions have the same exact rate of change. Okay. Looking at two examples, or actually 4, I believe. We have, does the set of data shown below represent a linear function? Justify your answer. So again, remember, to find your linear function and to realize what it is, you have to find all your delta x's and you have to find all your delta y's. So your first step is to determine the finite differences between successive x values and successive y values. So right here, your delta y would be 17 minus 11, which is 6. This next delta y would be y2 minus y1, 23 minus 17, which is 6. This next delta y, y2 minus y1, would be 29 minus 23, which is 6. And this fourth delta y would be y2 minus y1, 35 minus 29, which is also 6. Okay? So far all of our delta y's are the same, so now we just have to check our delta x's. Delta x would be 1 minus 0, which is 1. Delta x equals 2 minus 1, which is 1. Delta x equals 3 minus 2, which is 1. And delta x equals 4 minus 3, which is 1. So, notice that all of our delta x equal 1 and all of the delta y equals 6. So then determine whether or not the ratios or the differences are constant. Because all of your delta y's were the same and all of your delta x's were the same, instead of finding the slope 1, 2, 3, 4 times, you only have to find it once, because your delta y over delta x would just be 6 over 1, which is 6 for all delta x's and delta y's. And delta x and delta y were constant, so we can do this. And then, just because of the fact that they were both constant throughout the whole thing, that says yes, it is a linear function. Yes, because delta x and delta y were constant, so our slope delta y over delta x was constant. And this is what our question was asking us. Is it a linear function? And justify your answer. Why? Just explain as to why it is. Or why it isn't. So looking at this next one, notice the step is the same. Determine the first differences between successive x values and successive y values. Okay, doing the x's, since they're a little bit easier, delta x is 1 minus 0, which is 1. Delta x is 2 minus 1, which is 1. Delta x is 3 minus 2, which is 1. And delta x is 4 minus 3, which is 1. So far all of our delta x's are constant. Delta y would be 15.5 minus 17, which is negative 1.5. And we always take the second minus the first. Delta y between these two y values would be 14 minus 15.5, which is negative 1.5. Okay, we're still doing good. Delta y for this next one would be 11.5 minus 14, which is negative 2.5. Notice we got a different delta y. So let's check this last one, which would be 10 minus 11.5, which is negative 1.5. So all of our delta x was 1. But notice that delta y, we had 3 delta y's that equal negative 1.5 and 1 delta y that equal negative 2.5. That just means that when we're determining whether or not the ratios of the differences are constant, because delta x was constant, but delta y was not constant, the ratios are not all the same. So delta y over delta x will not be constant. And to be a linear function, you have to have a constant slope throughout the whole thing. So then when we determine whether or not the set of data represents a linear function, we would say no. And we have to justify our answer. Because delta y was not constant when delta x was. And that would be it. We've stated whether or not it's a linear function. We have given our explanation as to why we decided on our answer. Alright, now looking at example number 3, for the data below, determine if the relationship is a linear function. If so, determine a function relating the variables. Determine a function relating the variables just means write the function in slope-intercept form. So we're going to do what we've been doing. We're going to decide if this is a function by looking at if our delta x and our delta y are constant throughout the whole thing. Alright, so delta x would be 2 minus 1, which is 1. This next delta x would be 3 minus 2, which is 1. This next delta x would be 4 minus 3, which is 1. And this last delta x would be 5 minus 4, which is 1. Okay, our delta x's, all of our delta x equal 1. So then delta y would be y2 minus y1, which is 10 minus 7.5, which is 2.5. And then this delta y would be 12.5 minus 10, which is 2.5. This delta y would be 15 minus 12.5, which is 2.5. And this last delta y would be 17.5 minus 15, which is 2.5. Okay, all of our delta y equal 2.5. Alright, so all delta x are constant, and all delta y are constant. So then delta y over delta x would be 2.5 over 1, which is 2.5. Which this part is actually right here. But step 2 is just determining if all of your ratios are constant, all of your delta x are constant, all of your delta y are constant, then all ratios, all delta y over delta x are constant. So then delta y over delta x would be 2.5 over 1, which is equal to 2.5. So then the slope is 2.5. So remember I said we were going to write this in y equals mx plus b form, or f of x equals mx plus b form. We have the slope, and now we need to know what is our starting point. So let's go back and look. We started at 1, 2, 7.5, and 10. These are our first two coordinates. We need to know what is our y coordinate when x is b, when x equals 0. So if this delta x was 1 minus 0, which is 1, and this, remember, all of our delta x had to come out to be 1. And all of our delta y's had to be the second one minus the first one, and come out to 2.5. So then this delta y would be no difference, and 7.5 minus b would have to give you 2.5. Going off to the side with that, we have 7.5 minus b equals 2.5. Now we're going to solve for b. So we're going to start by isolating b and subtracting by 7.5 on both sides. So to isolate b, we need to get it by itself. So we need to subtract by 7.5 on the left. But because this is equality, what you do on one side of the equation happens to the other side, and 7.5 minus 7.5 cancels out to 0. So then that would be 0 minus b equals 2.5 minus 7.5 equals negative 5. We need b to be positive. So I'm going to multiply on both sides by a negative 1. Negative 1 would cancel. Negative and a negative cancels. So that means b equals 5. So if your slope equals 2.5 and you know b equals 5, and you're trying to write this in y equals mx plus b form, then substitute your slope and starting point in, and you would get y equals 2.5x plus 5. And if you were to graph this, you would find all of these points along the line. That is the answer. Okay, let's look at one more example. So it says, for the data set below, determine if the relationship is a linear function. If so, write a function in slope-intercept form relating the variables. So again, we have to find our delta x's and our delta y's. So delta x is 4 minus 2, which is 2. Delta x equals 6 minus 4, which is 2. Delta x equals 8 minus 6, which is 2. And then this last delta x equals 10 minus 8, which is 2. All of our delta x's are constant. Let's check our delta y's. Delta y equals 21 minus 22, which is negative 1. Delta y equals 20 minus 21, which is negative 1. Delta y equals 19 minus 20, which is negative 1. And then delta y equals 18 minus 19, which is negative 1. So notice that all of our delta x equaled 2, and all the delta y equaled negative 1. So then, delta x was constant, and delta y was constant. So delta y over delta x is constant. Now then, delta y over delta x, all of our delta y was negative 1, all of our delta x was 2. So then our slope is just negative 1/2. Okay, we have our slope. Now all we just need is our y-intercept. So if to get from 4 to 2, all we did was 4 minus 2 to get 2, then delta x 2 minus 0 would be 2. Yes, it matches up with the rest of our delta x's. So if our delta right here was 21 minus 22 to get negative 1, then it'd be the same for this delta y, and 22 minus b would have to give you negative 1. Well, 22 minus b equals negative 1. Let's isolate the b, subtract by 22 on the left, so you have to subtract by 22 on the right. That gives you negative b equals negative 23. Again, we have to have a positive b, So the only way to cancel out a negative is by another negative, but we don't want to change our b value, so we're just going to multiply by a -1. That turns that positive, but it also cancels out this other negative on the other side. So then we get that our b is 23. So if we have our slope at -1/2, and we have our b at 23, and slope-intercept form is y equals mx plus b, then plugging in m and 23, we would get that y is -1/2 x plus 23. And that's all we'd have to do.